Everyone, welcome to the 2024 season of One Word IAMP Mathematical Physics Seminar. As you know, this is a regular event hosted by IAMP, the International Association of Mathematical Physics. Before going on, let me make an announcement. So probably as you may know, Kasia Reisner, who had been an organizer since April 2021, stepped down at the end of last December, and she's now the president of IAMP. So thank you, Kasia. We all appreciate your contribution. Do you want to say something?
Thank you. Thank you very much. It was really a pleasure to be one of the organizers, and I will continue to be a regular still. I think this is very important that we keep doing intense. So Wojciech Dywalski, who's going to take over, is surely going to do a great job.
Okay, yeah.
But thanks for all the work and all the time we had together organizing it.
Okay, yeah, thank you, Kasia, also for introducing Wojciech with proper accent. So Wojciech, you want to say hello to everybody?
Hello, I am Wojciech. I think it's great that I can join this organizing team, and I will do my best to keep this seminar running. Yeah, so I'm really excited about the coming year. Thank you.
Yeah. Thank you. So we are excited to work with you. Okay, so now let's go to today's seminar. So today it is our great pleasure to have Chuck Newman as the first speaker in 2024. And today, as you know, he's going to tell us about the Riemannian hypothesis. Okay, Chuck, the floor is yours.
Okay, thank you very much. Thank you for inviting me. As I said before, I'm not going to, unfortunately, I'm not going to discuss a solution to the Riemann hypothesis, but some ideas that might be useful in working on it. Okay, let's see if I can know what to do. No, that's not right. Okay, so this is a kind of a preview of the whole talk. There are three topics that I want to discuss, how they're connected to each other or might be connected to each other. One is Riemann hypothesis, RH, over here. What does something is not exactly. Well, all right, I guess I'll live with this. The other is Brownian excursions, BE, and the other topic subject is our Ising models. So I want to talk about these three things and their connections or possible connections. So the left side connection, the one between the Riemann hypothesis and Brownian excursions, or at least things related to the Riemann hypothesis and Brownian excursions, is relatively well known, and that will be the first thing I'll be discussing. Although certain aspects are somewhat mysterious, which I'll comment on a bit later. The other two possible connections, that's I have possible in red because they aren't yet connected, between Brownian excursions and Ising models, or between the Riemann hypothesis and Ising models. If either of those two possible connections could be made an actual connection of the right sort, then you would have a link between Ising models and the Riemann hypothesis, either directly through this channel or sort of in two steps through this pair of channels. And if you had those right connections, then one could use the famous theorem of Li and Yang from 1952 about zeros of Ising model partition functions to actually prove the Riemann hypothesis. So I'll discuss these various things, some of them are more known than others. Okay. Right. So this is a kind of survey of the talk, and I guess I'm going to start with this fairly well-known connection in the next slide, and then well, no, actually, I guess I'll start with just some classic things about the Riemann zeta function and the Riemann hypothesis, and then talk about this fairly well-known connection. Then after that, I'll discuss, I think, the connections between Brownian excursion and the Ising models. Possible connections. Well, I forget which order. Anyway, the other two sides of the triangle. Okay, let me. Somehow I've lost. Okay. Okay. So I'll begin with some standard facts about the Riemann hypothesis, which is based on the Riemann zeta function, which is just to begin with is expressed as this simple infinite series that we all learn about in calculus, or maybe in some countries we learn about it in elementary school. This is an infinite series, first defined for real values of the parameter s bigger than 1, where it converges. So that begins to be defined only for real s bigger than 1. But it's a standard fact that it can be analytically continued to the complex plane without any work at all to the half of the complex plane where the real part of S is strictly bigger than 1. But it has a pole. It has actually a simple pole at 1 where this series diverges. But except for that simple pole, it can be analytically continued to the entire complex plane, except for the pole at 0, at 1, and as an analytic function has zeros and has to have zeros in various places, it has some so-called simple zeros at the negative even integers, and it's known that all the rest of the zeros are in the critical strip, which is the real part of S, strictly between 0 and 1. And the Riemann hypothesis from 1859, if memory serves, is simply the statement that the rest of the zeros, not counting these simple zeros over here, are right in the middle of the critical strip on the critical line, which is a real S equals 1/2. So there's a standard modification of the Riemann zeta function to give the Riemann xi function, which is defined here. You multiply the zeta function by a gamma function. So the gamma function has some simple poles exactly at the places which will cancel the simple zeros of the zeta function. This pi to the minus s over 2 is there because it somehow, as we'll see shortly, somehow increases the symmetry properties of the xi function. And then these extra factors, the s minus 1 is a 0, which will kill the pole of the zeta, the simple pole of the zeta function at 1, and the s, which has a 0 at 0, that kills a pole of the gamma function. So this function is now a standard fact is that this xi function, which is a kind of modified zeta function, is an entire function, and it's gotten rid of the simple zeros, and all its remaining zeros are in the critical strip. So the Riemann hypothesis in terms of the xi function is that all of those zeros, which are all in the critical strip, are in the middle line of the critical strip at real part equals 1/2. So it's convenient to translate by the 1/2, taking that critical line to the imaginary axis, and that's the function xi of 1/2 plus z. So I'm writing z because we want to think of it as a complex variable. And there's another standard fact that function can be written as a two-sided Laplace transform of a certain somewhat funny-looking function, capital psi of x, written here as an infinite series. All these are very, very classic facts. And the infinite series is just written down in explicit form here. Sum from n equals 1 to infinity of this product of two factors. One of them, which is for a given value of x, is very rapidly decreasing in n, and the other one is a polynomial in n, so it's certainly a convergent series for any let's say real value of x. So we'll be talking a lot about this function. There's a famous identity involving called the functional equation for the zeta function, which re-expressed in terms of the xi function is simply the statement that xi of s is xi of 1 minus s. And because of this translation by 1/2, that becomes, in terms of this function, capital psi is the fact that this function psi is an even function of x, even though it doesn't look like it from this formula. Or I should say, it's not at all obvious from the formula that it's an even function of x, but that's a standard fact, well known and equivalent to the so-called functional equation for the xi function. In the next slide, I'll show you the graph of this function psi. The graph will certainly look even, well, the graph is not quite a function of psi, but for some reason having to do with where the slides came from, it's a slightly transformed version in which you scale the u by a factor of 2 and multiply the whole thing by 1/4. But anyway, still the evenness of psi is equivalent to the evenness of phi, obviously. And I'll show you this graph in a second, but the Riemann hypothesis is the statement that the Laplace transform of this psi function, that's over here, which is xi of 1/2 plus z, all its zeros should be on the pure imaginary axis, because that's because of the 1/2 that corresponds to the critical line back in the original variables. Okay, so I'll show you the graph of phi in a second, and recall several times that the Riemann hypothesis is equivalent to the statement that the zeros of its two-sided Laplace transform are all pure imaginary. Okay, so let's take a look at the graph. So that's the function capital phi. That was a funny looking infinite series. So it's nothing very terribly striking about it. It looks roughly similar to the graph of the standard normal density function. It has a single mode. The graph certainly looks even, and better be, because it is supposed to be even. Because of that exponential of a minus exponential factor, it goes to zero much more rapidly than the normal density does. So already by around 0.4, it's extremely small value, or minus 0.4. But otherwise, it's nothing very striking about this graph. But somehow, this particular function with this particular graph, the Riemann hypothesis is equivalent to the statement that its two-sided Laplace transform has only pure imaginary zeros, and that's what that's the version of the Riemann hypothesis that we'll focus on for the rest of the talk. Okay, so I don't know if there are been any questions, since I'm not looking at the chat, but if there are any, somebody could tell me and I could try to say something about them. Okay, otherwise I'll go to the next slide. Okay, so remember there were three connections or possible connections we wanted to talk about. The first one we'll be discussing is the connection between the Riemann hypothesis and Brownian excursions. So because we've expressed the Riemann hypothesis in terms of this function psi of x, so this connection has to do with how the function psi of x shows up in Brownian excursions. So first, I want to make the following comment. This function psi, whose graph we just looked at, is non-negative for all positive x. In fact, strictly positive. It says here that, and which I'll explain in a moment, that it's easy to see that using the fact that psi is an even function, which we discussed. So let me go back to the formula for psi. That's over here. Here it is. Yes. So so how do we know that this is I mean, the graph looks positive. That's best one can tell. But how do we know that? How do we show that this is a positive function? Well, it's the following argument. If you look at positive values of the variable x, then you can check rather easily that each of these prefactors, this difference of two things, is in fact positive. So the first term is always bigger than the second for every positive integer n. And that's when x is positive. So the e to the 9x over 2 outweighs the e to the 5x over 2. And then you can check that the first of these two terms is bigger than the second. And so it's term by term positive. That's when x is positive. When x is negative, that's not true that it's term by term positive. But we already have discussed the fact that psi is an even function. So if you prove that it's positive for positive x, it's automatically positive for negative x, and that's the argument. Okay, so that's the explanation of this comment, that it's easy to see that it's a non-negative function using this evenness. Okay, now it's also because that's the last factor. Let me again go back. this last factor is very rapidly decreasing and sort of outweighs these prefactors. It's clear that for large x, it's going to behave more or less like this. Actually, this for n equals 1, so it's going to go to 0 like e to minus an exponential. So that's true, and here's a more precise statement. That's clear when x is large and positive. It's bounded by something like this, and for negative x, again, you use the evenness. So you get that this function of x written as a funny-looking infinite series is a very rapidly decreasing at both plus and minus infinity. And it's as we said before, it's non-negative. So so if you multiply by the right constant to normalize it, you can regard it as a probability density. So that's what I want to do, and I'll define x sub capital psi to be a random variable with that probability density proportional to this function psi of x. And remember, the Riemann hypothesis was equivalent to the statement that the two-sided Laplace transform of this function has only pure imaginary zeros. So in more probabilistic language, that two-sided Laplace transform is just the moment-generating function of the random variable with psi of x proportional to its probability density function. So therefore, the Riemann hypothesis in this language is that there's a certain random variable with certain distribution, a certain density, and the Riemann hypothesis is equivalent to the statement that the zeros, all the zeros of its moment-generating function are pure imaginary. Okay, so so now that we're sort of working in kind of probabilistic language of random variables, moment-generating functions, can discuss the relation to Brownian excursion. So let me first tell you or remind you what a normalized Brownian excursion is. Actually, I'm sure there are people here who are much more expert in that than I am. But roughly speaking, the Brownian excursion is something you get from you could start with a standard Brownian motion. One thing one does with Brownian motions is the Brownian motion starts at 0 at time 0, but you could sort of force it to be to go back to 0 at time 1. That would give you a Brownian bridge, but a Brownian bridge would equal 0 many times between 0 and 1. A Brownian excursion, we want something which looks like a Brownian motion, except like a Brownian bridge at 0 at both time equals 0 and time equals 1, but in between it's not 0, and standard to choose it to be positive, strictly positive. So there are various ways to define it, but I think it's enough to say that it's like a Brownian motion, except constrained to be strictly positive and return to 0 at time 1. And there's some standard normalization which I never remember specifically, that gives you the normalized Brownian excursion. So that's the object that one wants to talk about. It's a standard object in stochastic process theory or Brownian motion theory. Okay, now what's the relation between this Brownian excursion and this random variable xi, or its distribution or density that's proportional to this function psi? Well, it's the following. If you look at the maximum of the Brownian excursion, that will be some strictly positive random variable. soup of the Brownian excursion between time 0 and 1. That could be small, could be large, strictly positive, and normalize it by this factor, square root of 2 over pi. Then you still have a random variable y, which is strictly positive. We're looking for a random variable which has this psi function as its density, which is an even function on the real line. So we don't want something strictly positive. Take the log of this scaled maximum of the Brownian excursion. That's something which could be positive or negative, because the Brownian excursion maximum could be small or could be big. That random variable x almost has its density is almost exactly equal to psi. That's not quite right. In fact, it differs from psi by a simple exponential factor, e to the minus x over 2. So leaving out constants and things, basically the log of the maximum of the Brownian excursion has a probability density that is almost exactly this strange specific function capital psi, up except for this extra exponential factor. That formula for the density of the maximum Brownian excursion, or its log, was actually first determined by in 1976 by Douglas Kennedy. When I see Kennedy, I want to say Tom Kennedy, but it's a different Kennedy. In 1976, and a good reference is a review paper about different Brownian motion things from 2001 by Bian, Pittman, and Yor, which includes the statement and maybe also derivation of this result of Kennedy from 1976. Now, we said before that it's known fact that this function, capital psi, is an even function, even though when you look at the formula, it doesn't look particularly even. And so, well, that's still true when you get the psi as something related to the distribution of the maximum of Brownian excursion. But the derivation of the derivation, the number of derivations of this evenness, which is equivalent to the functional equation for the zeta function, but they're not very probabilistic. That is to say, not probabilistic in the sense of being something related to the probabilistic properties of the Brownian excursion. So it seems to be a bit of a mystery in the sense that since this quantity is now, this object, this random variable, is now expressed in terms of Brownian excursion, to find a probabilistic explanation related to Brownian excursions for why you have this evenness property. That might be useful. I'll come back to that later, because when we talk about possible connections with Ising models, the objects, the distributions one gets from the Ising models, the kinds of Ising models that we'll be talking about, automatically have this evenness, the symmetry of their distributions. And so if one found a probabilistic explanation for the evenness of this Brownian excursion object, maybe a route for doing that would be somehow, finding a relation to Ising models, which is another one of the legs of that triangle from the beginning. Okay.
Yeah, Chuck, can I ask a question? So
yes, please.
so this correspondence looks just like a miracle to me. So this is a Brownian excursion, and it seems that this has nothing to do with this theta function and anything. But is it possible for these people to conjecture this kind of thing? And are they natural in some sense?
So I'm not quite sure. I mean, the derivation of the formula for the distribution of the maximum of the Brownian excursion was done in 1976 using Brownian motion methods, and a specific formula was obtained. I wasn't noticed, I think, until some years afterwards that it had anything to do with the Riemann zeta function or the Riemann hypothesis. So there's certainly probabilistic derivations of the fact that this particular distribution arises in Brownian excursions, but the evenness of it that doesn't seem to have a direct probabilistic explanation in that setting. That's the thing I was trying to.
Yeah, okay, yeah, that's I understand. Yeah, thank you.
Okay, any other questions? Okay,
I have a question.
yes.
It seems like this looks a little bit like a conformal invariance or covariance property, but in the target, it's not a time parameterization. But does that help at all? Do people try to understand the mystery this way?
I don't know the answer or to that question. I don't think. I don't think informal arguments were used in these probabilistic derivations of the formula for the distribution, as far as I know. But maybe that's a good idea to try to do that. Yeah, so I'm not sure if that was more of a non-answer to your question, but that's the best I can do. Okay. Right. All right. So yes. So okay. So we've discussed the first of the three sides of that triangle, the one where actually connection exists, which is there is a relation between Riemann excursions and the Riemann hypothesis, in the sense that same function psi arises, although why it does is a mystery, and properties of it are a mystery. But now these other two lines are only possible connections. So one of them was a possible connection between the Riemann hypothesis, or the zeta function, and Ising models. So that I'll discuss now for a while. Probably everybody in this audience knows about Ising models, but these transparencies were first written for a non-statistical physics audience. Anyway, let me remind you what an Ising model, or here it's called an Ising system, is. It's a collection of random variables, n of them. This is a finite Ising model, a pair of ferromagnetic interactions. It's n random variables taking values +1 or -1. That explains this product measure. If there were no couplings, then you would have independent + or -1 valued random variables, and the joint distribution would be just a product of the measures giving probability 1/2 for +1 or probability 1/2 for -1. That would be this product measure. But the Ising model has couplings, it has interactions, and so you modify this product measure, which is the appropriate measure when the inverse temperature is 0 or the temperature is infinity, by a Gibbs factor, which is of the form exponential of a quadratic expression in the Ising variables, and the coefficients for a ferromagnetic Ising model are all non-negative. So when you have such an Ising system, collection of +/- 1 random variables with such a joint probability distribution, then the theorem of Li and Yang applies, and a kind of special case of it, or corollary of it, says that if you says that if you take a non-negative linear combination of these Ising variables, so these coefficients here are allowed to depend on J and N, a non-negative linear combination, then that random variable, its moment generating function, which is a kind of partition function in the variable Z, which is like a magnetic field variable, all of the zeros of that moment generating function are pure imaginary. So the original theorem of Li and Yang was stated in somewhat different variables, so the zeros were on the unit circle, but in these, those are the lattice gas variables, but in terms of the Ising variables, it's in this kind of magnetic field variable Z, it's that the statement is that all the zeros are all pure imaginary. So that's a kind of a corollary of the more general theorem of Li and Yang from 1952. Okay, that's the version which I'm interested in. So to try to find a connection between Ising models and Riemann hypothesis, or said a little more impressively sounding, to try to find a proof. If you wanted to find a proof of the Riemann hypothesis using Ising models and the theorem of Li and Yang, the natural way to try to do that would be to find a sequence of Ising models with this n is the parameter of this sequence. So the size of the Ising system would be increasing with n. Find some ferromagnetic couplings, and then find some non-negative averaging coefficients, so that this sequence of random variables, magnetization random variables, would converge in distribution to the random variable whose probability density is proportional to this funny function psi that we wrote about. So let me make an elementary comment first. Before you take a limit, you're taking a linear combination of plus or minus one valued variables. So this W super n would only have finally many variables. Its distribution would be some sum of point masses, some sum of delta functions somewhere. So obviously it couldn't have this continuous density as a distribution. But when you take a limit as n goes to infinity, then you possibly could have a limit which has a continuous distribution with a nice density. And if you're very clever or very lucky, you might be able to do that in such a way that the limiting density is exactly proportional to this function capital psi that we wrote down before, related to the Riemann hypothesis. If you succeeded in doing that, then you would basically be finished, because you know that the zeros are all pure imaginary before you take the limit, and stands to reason that after taking the limit they would still be pure imaginary, and there actually turn out to be no technical issues. There's a theorem that appears in a paper of myself and Wei Wu from a few years ago, which says that ordinary convergence and distribution, so that of the usual sort, namely that the equivalent to that, the Fourier transform on the real line converges pointwise. Ordinary convergence and distribution of that sort, which is sort of the weakest kind of convergence of random variables that you have in probability theory, is sufficient so that the limiting distribution will have the real pure imaginary zeros property for its moment generating function. So if you could do this, find some sequence of Ising models, couplings, and averaging coefficients so that this magnetization type variable would converge in distribution in the ordinary sense to the random variable who's with this psi as its density, then the Riemann hypothesis would be a consequence of basically the theorem of Lee and Yang and this limit construction. Okay, the only problem is nobody yet has figured out how to find such a sequence of Ising models and averaging coefficients. So you have to find these things to get the right limit. So later on, not next slide, but a few slides from now, I'll maybe the more or less the last slide I'll do. I'll discuss some well, maybe failed attempts isn't right, but some examples in which you can get in nice limiting distributions with nice limiting densities, ranging from very elementary cases to not so elementary cases, but unfortunately, so far none of them has given you this psi as the limiting density. But we'll just to see some kinds of limiting distributions you can get, we'll talk about that a bit later. That's only actually just 2 slides from now. How much time do I have left?
Well, I think you can speak like 20 minutes.
Okay, that's
We are not strict. Yeah.
Well, yeah, it's also more than I either need or will actually use, I think. Okay, so so that last slide had to do with the possible connection between Ising models and the Riemann hypothesis, and we'll come back to something related to that in the next slide. But then we haven't yet talked about this third line of the triangle, the possible connection between Ising models and Brownian excursion. So this is almost everything here. Is something that much of what's on this slide is things I mentioned before. So the first 2 lines here is just a reminder. The Brownian excursion B of t is related to this specific function psi by this. If you take the sup of the Brownian normalized Brownian excursion, scale it by square root of 2 over pi. That's a random variable which is strictly positive. Then you take the log of it, which can be positive or negative. That gives you almost exactly this specific funny looking infinite series function capital psi, except for this exponential, simple exponential factor and normalization constant. So that's a fact. That was the thing that was derived by Kennedy, Douglas Kennedy, but without knowing anything about the relation to the Riemann hypothesis. Right. So when you look at Ising systems, because of the obvious invariance for the Ising model, when you change all the spins to their negatives, because in the Gibbs factor, the thing that appears is the quadratic expression in the spin variables. If you change all the spins to their negatives, the two minus signs cancel, and so you haven't changed the Hamiltonian and the Gibbs factor at all, and so that you have the symmetry property automatically. So any limiting density of the kind we talked about in the last thing will have to be an even a symmetric distribution. Will have to be a even distribution, and if it has a density, it's an even density, as is the function psi. But as I said before, when you find the psi appearing in the log of the maximum of Brownian excursion, this symmetry property seems to be a bit of a mystery. It's known because it can be derived in various ways, but it doesn't have it doesn't seem to have a direct probabilistic explanation. Unlike in the case of the Brownian motion in the Ising model situation, when you take these magnetization variables and their limits, you all along you had the symmetry property because you had that trivial symmetry property for the Ising model. So that's that's just the opposite of a mystery. That's an obvious fact. This possible connection is simply a wished for connection. Could one find some direct relation between Brownian excursions or logs of logs of maximum Brownian excursion and Ising models, which, among other things, would help explain this? That could be an explanation of this mysterious symmetry property, because in the Ising model context, it's not a mystery. It's a direct probabilistic explanation, which we just gave here because of the nature of the Gibbs factor and the fact that the Hamiltonian is quadratic. If one could find some relation between Brownian excursions and Ising models or logs of Brownian excursions, as a byproduct, that might give you a sort of direct kind of probabilistic explanation of the symmetry. But even better than that, it could help prove the Riemann hypothesis, because one has the Lee and Yang theorem for Ising models. If one found the right connection between Brownian excursions or logs of maximum Brownian excursion and Ising models, that could allow you to import the Li-Yang theorem result to the Brownian excursion setting, and hence to the Riemann hypothesis setting. So that's what this thing at the bottom is saying. So this is there's no, I'm not aware of any evidence at all that there is any such connection, and it would be a somewhat have to be somewhat complicated connection, because you also have the log and the soup to deal with. But anyway, it's a question. Okay, so if there aren't any comments or questions so far, I'm going to go to the next slide, which is actually basically the last one, which is the one that I mentioned before, which gives some examples of limiting distributions and densities one can get from Ising models, none of which so far have given the one that you would like, which is the distribution that has this capital psi as its density function. Okay, so this is just a one slide which gives a number of examples ranging from totally elementary to not elementary at all, and then a sort of somewhat strange suggestion at the end. anyway, these are by examples of limiting distributions with densities, which automatically will be symmetric even densities that you can get from different Ising systems. Okay, so none of these so far have given rise to the function capital psi that one would like to get. If they had, you would have heard about it. Right, so the most trivial example is if you take each of your Ising systems to have zero couplings. So then the spin variables are just independent plus or minus ones. Then you can simply add them up, multiply by 1 over square root of n, and use the standard central limit theorem and get a limiting distribution, which is the distribution. And so the limiting distribution has a density, which is of the form, depending on how you normalize things, density of the form quadratic, constant e to the minus constant times w squared, or w is the variable in the limit. So that's a completely trivial example, but at least it shows that the fact that things were discrete before you take the limit doesn't mean that the limit the limiting thing can have a nice continuous density, and the Gaussian density is certainly nice and continuous. Okay, so that's a completely trivial example. The next simplest example corresponds to the Curie-Weiss model. That's a model in which you take all the couplings to be the same, for all I and j that have the same coupling. If there's a parameter b in here, if you set that to be 0, think about that case first. You simply take the coupling to be a constant over n. That's the Curie-Weiss model. The constant is the inverse temperature for the Curie-Weiss model. All the spins are coupled to each other equally. And the critical value of that parameter is 1 in the way things are set up here. So one chooses that critical parameter. That gives you the interesting limit case. So if this little b is 0 and you take the couplings to be beta critical over n, which is just 1 over n, then if you take the sum of those Ising variables and scale it not by square root of n, but if my memory is right, it's n to the 3/4 because they're more strongly coupled, then the limiting distribution is proportional not to a Gaussian expression, but we're taking a little b equals 0 at the moment. It's proportional to e to the minus the 4th power of the variable w. So that, of course, is that's the famous a result of Barry Simon and Bob Griffiths showing how you can relate 5 to the 4th lattice field theories to ferromagnetic spin 1/2 Ising models, and it was basically because of this limit. That's with a little b equals 0. Incidentally, the fact that the Laplace transform of e to the minus w to the 4th over 12, or this modified version here, has only pure imaginary zeros. That was already known by Polya in the 1920s or 30s, not using Ising models, just by some other direct arguments. Now, so to fill in the rest of this line, if instead of taking 1 over square root of n as the couplings, you modify that a little bit, then that's the kind of near critical scaling limit. So the right way to modify it is by constant over square root of n. And then that modifies the eta minus constant w to the fourth by a quadratic factor, and giving you this as the limiting distribution. So these, that also, the fact that its Laplace transform is also with the b not equal to 0, a b can be positive or negative. That was also known by Polya. Anyway, so that's another example of a nice continuous limiting density one can get from Ising models. Okay, then the next, well, in a way, the thing that's in this line of reasoning, the next example really should be the number 4 here, but let me instead do number 3. So this is going, so this is going to everything equally coupled. Here, nothing was coupled. So now we're going to do a kind of one-dimensional coupling. So you can think of a nearest neighbor Ising model in one dimension on the one-dimensional lattice, and where the couplings are just a constant times. This is the function which is 1 when I and j are nearest neighbors on the line. So that's the one-dimensional nearest neighbor Ising model. No, that's also have a Liang theorem applies there, and you can take limiting distributions, and if you take the nearest neighbor Ising model on the line, and if you think of the variable in the line instead of being space, to think of it as time, and then if you change the time instead of one distance unit time, you think of it as a small time, then you can take a limit in which you get a continuous time, a limiting process, and because on the Ising model on the nearest neighbor Ising model on the line is just a macro process on the line, which stays, say, +1 for a while, and then at some point flips to -1. You obviously could scale it in such a way that scale things in such a way that in the limit you get a continuous time. The time is now the one-dimensional spatial variable, plus or minus one valued process. So that is to say, the standard plus or minus one valued stationary jump process on continuous time, let's say time running from -infinity to infinity, that's a limit of nearest neighbor one-dimensional Ising models. So it will have so you can, the Liang theorem for the one-dimensional Ising model, in the limit will apply something about zeros of moment generating functions. And in particular, it would say that if you take this stochastic process, integrate it with a positive test function, that's because the Liang theorem applies to non-negative linear combinations of the Ising variables. So I want this function h of t to be non-negative. This gives you a random variable as long as this h, you want this test function h to be non-negative, it should go to 0 so rapidly enough that this is a well-defined random variable. And any such limiting distribution will have its moment generating function having pure imaginary zeros by the Riemann hypothesis. If you want to use, if you would like to try to prove the Riemann hypothesis using the one-dimensional nearest neighbor Ising model, then your question is simply the following: is there some choice of this non-negative function h so that this random variable has a probability density proportional to the specific function psi, the one that arises in the Riemann hypothesis? If that were the case, if you could find such an h, that would prove the Riemann hypothesis. It would be a surprisingly, in a certain sense, elementary proof of the Riemann hypothesis. And because my gut feeling is that that would be too easy. That's why it says doubt it. That means I doubt that this is possible. I'll make a few more comments about this. One thing you need to do is get a limiting a distribution whose probability density decays like e to the minus an exponential. Now you can certainly arrange to have things which don't do that. So, for example, if you took this h of t to have compact support, that would make this integral a bounded random variable. Say h is a bounded function with compact support, then this would become a bounded random variable, and the bounded random variable that decays. You could arrange to have it having a density function, but that decays too fast. It's zero after a while, so it's not the one we're looking for. You could surely. I haven't pursued this since I doubt that it would end up helping things. I mean, helping the Riemann hypothesis, but you surely could pick an h which goes to zero, is not compact support, but goes to zero in a carefully chosen way, so that the tailed behavior of this limiting probability density would look like e to the minus e to the 2x, or whatever you want for the tail behavior. So you could surely do that, but that's not, you don't want just the right tail behavior. You want a specific limiting density, and that's what you would need to do. It might be amusing if for somebody to prove that, which I think is the case, that no choice of h can give that psi. That's a no-go theorem, saying Ising models may be a good approach, but not one-dimensional Ising models. So I'm not aware of such a proof. It would not be a major result in the subject, but it would certainly be a little interesting. Okay, let me go on to the next case. So this is something which is fairly non-trivial. It also doesn't lead to the psi that you want from the Riemann hypothesis. That's instead of taking nearest neighbor Ising model in one dimension, you take the nearest neighbor Ising model in 2 dimensions. That's non-trivial Ising model. So here they're just defining it. Unless the couplings are nearest neighbors in Z2, you get 0, and otherwise it's let's say a constant. If you take that constant to be the critical value that corresponds to the critical temperature, then that is the 2-dimensional, and take the infinite volume limit of that. That's the 2-dimensional nearest neighbor critical Ising model. You can take a sum of a block variable, sum of the spins in a say a square, divide by the right power of the length of the square, which is something like the 5/6 power, maybe, and then study that limit. One knows that the limit exists. One even knows that it has a density. One even knows some properties of the density. One knows enough properties to know that it is not the density psi that one wants for the Riemann hypothesis, because it's known that its tailed behavior is not e to the minus exponential. It's actually e to the minus this constant times the 16th power of the variable x, and that's an interesting fact that appears in one of the papers of Federico Camilla, Christoph Carbano, and myself from about 8 years ago. But it shows that it's not the it's not the Riemann hypothesis psi that one wants. One could try to do something more sophisticated with the two-dimensional Ising model. Instead of taking just the sum of the things in a block, one could take some smoothing function, some way that would be a little bit like what's doing here with this function h of t, but this would now be a function on R and sort of an R2. My guess there is that wouldn't work either, but I certainly don't have a proof it doesn't work. My general thought about this is that rather than trying to be clever with these test functions h, one needs to find the right Ising model with the right critical behavior at or near its critical point and try to study that. And a kind of wild idea is that maybe one should look at one-dimensional long-range Ising models of the 1 over distance squared type of interaction. Those have strange critical behavior. Maybe it's strange enough that has a chance of giving something related to the Riemann hypothesis. But that's more of a dream than a proposal. This actually is more or less the end of my slides. So thank you for listening.
Thank you, Chuck, for the beautiful and exciting talk. Okay, so any questions or comments? Probably can I start? Okay, so
Sure.
yeah, thank you, Chuck. This is really exciting. But so the main object from the Ising model is this W, which is basically the magnetization. But this W is not just a random variable, but it satisfies many relations, many correlation inequalities like the one proved by you, right? So this means that, W, the moment of W has some constraints. So is it, so have anybody tried to look at this psi function and try to examine if this psi function satisfies these constraints coming from correlation inequalities about the moments?
Okay, so I have one small partial answer to that. So a long time ago, I don't remember the precise reference, quite a long time ago, I once tried to do something of that sort in order to disprove this idea, which the reasoning was the following. Okay, if you have something which is a limiting distribution that comes from Ising models in the way we're talking about, one property you have is the Liang property, which is the thing that we like and that we're hoping would might lead to a Riemann hypothesis. But there are other things that you have. So, for example, another set of correlation inequalities are things related to the higher moments, like things like the Griffiths-Hirsch-Sherman inequalities, the GHS inequalities, which gives relations between the fourth moment and the other moments that are different than what you get from the Liang theorem. So so you can have things which satisfy, so to speak, the Liang property, but not the GHS inequality property. So I actually thought of that. This might be a way of proving that this approach using Ising models doesn't work, because maybe you can show that this function psi doesn't satisfy something involving fourth moments that you get from the GHS inequality, which it would have to if it came from an Ising model, but wouldn't necessarily have to for the Riemann hypothesis. So I attempted to do that. So I checked one property involving fourth and second moments that you would have to have from the GHS inequality, and I thought, well, if I can show it doesn't, this function side that doesn't have that, then well, that would rule out this approach. That would, that would be a shame, but at least it would save a lot of effort. Well, it turned out that it did satisfy that property. So I think I have a paper, pointing that out maybe. And it turned out the reason it satisfied it was something very simple, having to do with the location of the closest zeros of the zeta function. Was kind of the closest one was fairly far away from the real axis, and because of that, you somehow got this inequality about the fourth moments relatively easily. And that was a sort of a failed attempt to show that this method can't work. But I don't know of any other more sophisticated version than that. There may be some, but I'm not aware of it.
Yeah, thank you. That's very interesting. So any more questions or comments?
I have a question.
Yes.
Krzysztof Meissner. What if Riemann hypothesis is not true? What would that mean, for example, for the Brownian excursion, if it is not true? If there is a zero which is outside of the 1/2 line, very, very, very far away, what would that mean? Is it a disaster, or it is a problem?
That's an excellent question, I think. I don't think I have anything to say about it. My guess is that not much to say about it. My guess is that it wouldn't say very much, because as I mentioned before, the derivation of this formula for showing this function psi arises in the Brownian excursion was derived without any knowledge of any connections with the zeta function, or I mean with the hypothesis. And so it probably, if it's whatever it said about the Brownian excursion, it would be something very subtle, which would probably
but that
not
would
be
ruin, but that would ruin the connection with the Ising model. Yes.
Sure.
Well, it would. Yes. Yes. That's true.
So any connection would be forbidden in a sense, or I see. But for the Brownian excursion, it doesn't say anything. Okay.
Well, but this is the same function psi that appears in the actual Riemann hypothesis. So if you found a zero that wasn't where it belonged, you would have disproved the Riemann hypothesis. That's more exciting than showing you can't prove it.
Yes, that's for me far more exciting than if the Riemann hypothesis is true. So
yes. Okay. So yes. So okay. So let me see if I can. Yes. So yes. So that's I think that's a perfectly respectable idea. That if you want to try to disprove the hypothesis, and there's nothing wrong with that, because I think there are some serious people who think that is a valid possibility. So then this Brownian excursions could be a possible tool for doing that.
Yes, I collaborate with Roger Penrose actually for many years, and that's the idea that we discuss over and over again, that Riemann hypothesis is not true, and what would that mean for physics? So, but anyway, that's thanks for the very nice talk. Yes, thanks.
Thank you. So any other questions or comments?
Yeah.
Yes, please.
I'm not familiar with the Liang theorem for models, for spin models other than plus or minus one spins. So is there any other models for which Liang is known and one can play this similar game?
Yes, that's another good question. And should I get rid of my screen sharing?
Yeah, I can do that for you.
Oh, wait, I can do it also. Okay, good. Sorry. So yes. So there are yes, there definitely are other examples. So the two most well-known ones, well, I mean, two and a half well-known ones are if you replace the plus or minus one Ising variables by two parameter vector variables taking values on the unit circle. That's sometimes called the XY model or the classical rotator model. But if you, for a certain class of ferromagnetic type couplings, if you still pick one of the variables, like the X component, the one component of this two parameter spin variable, and take positive linear combination of those variables, that will still have this Liang property. I mean, the Liang, not the original theorem of Liang, but this Liang property applies to that model. That's a plane rotor or XY model. Similarly, it applies to the three-component version, in which the basic spin objects take values on the surface of the I guess it's S2, the sphere, two-dimensional sphere sitting in 3 dimensions. And again, if you pick one of the components and take positive linear combinations of those variables, its moment generating functions will have only pure imaginary zeros. Also, the partition functions for the quantum version of those two models also have the Liang type property. I think those are the main examples. So that
higher spin Ising, does it violate?
Yes, not. I don't think there's a Liang type result for. Well, sorry. Let me back up. A second. Yes. Sorry. Yes. So one component spins. Special cases, one component spin where the variables, instead of taking values +1 and -1, take values like +1, 0, and -1, or +5, +4, +3, blah blah blah, down to -5 with equal weights. Actually, the Liang theorem applies to those, and those can be actually derived starting from the standard Ising model Liang theorem by using similar methods to like what was used by Griffiths and Simon to get to e to the minus x to the fourth. The most general version of that, which was actually first proved by me, and then a more slick general proof was done by Lieb and Sokol, is that you could replace the still one-dimensional spin variables. You could replace the one taking values only +or -1 with equal weights, or the things I just mentioned, by any symmetric distribution you want, basically, as which goes to 0 at least, like fast as a Gaussian, or faster, which the moment generating function for that single random variable has only pure imaginary zeros. Then you could use that distribution for your spins, and then construct an Ising type model coupling those things together, and you will still have the general Liang type result for that that situation. So yeah, so you're free to put in anything you want for which you already have a Young property and type property, and build a Ising type model from those things to get more complicated things, and those will still have the Young property. In a way, there are too many possibilities. So I usually, think about the standard type Ising models just to restrict attention.
Yeah. Okay, so by the way, so Takashi commented that your answer to my question is already written in your paper from 97. That's true. So that's this weird that this is a probability theory in the related fields, which is now called, but it's called Zeitschrift something. Okay.
Oh, yeah, Zeitschrift for Wahrscheinlichkeitstheorie und unverwandte Gebiete.
Yeah.
My German pronunciation is undoubtedly terrible, but
You can
yes, the old name for probability theory and related fields.
Ja, Wahrscheinlichkeitstheorie.
Okay, that has okay, so any other questions or comments? Yes.
One more, but if someone else wants to go, they can go ahead. No?
Yeah, why don't you go, Malik? Yeah.
All right. Is the so you mentioned this exponent, this result with Camia and Garbon, where you get this exponent 16, if I remember correctly. So this is, I suppose, related to the exponent delta, the critical isotherm, right?
Yes, yes, I think that's right.
So I suppose what in the search for a candidate of what could be something that produces the psi, one could probably use like some very heuristic renormalization group type arguments to try to figure that out, or at least see if one of the R squared does satisfy that, or some other model.
Yes, in a way, that's one reason why I had that on my list as a possibility, because some non-rigorous normalization group calculations about that model show that it does have strange critical behavior.
Yes.
And so yeah, so that's maybe the main reason why I thought that could be a good candidate. But
Okay, so this is very exciting, but our time is limited. So any other quick questions or comments? Okay, so if not, let's thank Chuck for the great talk. Thank you very much.
thank you for
Thank you
having me.
everybody for coming and joining the discussion.